Yes.
Hey, I'm sorry.
We are there.
Yes, I will get you.
I had some technical problems, so I delayed to sign in. But now I'm on. Good evening to you all, wherever you are. Some of you are in Port Portal, some of you are in Mbarara, some of you are in Kampala. I'm not in Kampala, but I'm on the outskirts of Kampala, in Wakiso district. And I think the network problem that actually made me delay. But now that we are connected, we can go ahead and see what. Last time it was flow of fluids, but now we want to see what effect heat has on the flow of fluids. And this is heat transfer. I've prepared this. Are you hearing me clearly?
Yes, sir. Yeah.
I've prepared this in line with what we are supposed to do as pharmaceutical engineers. Pharmaceutical engineers, there is a lot of calculations which you may not indulge so much into, but at least if you can master it, it will be of big help in case you are assigned some duty to look at some of the heat transfer mechanisms in the process of manufacturing, pharmaceutical products. So in this case, we are on heat transfer. Now, the definition of heat transfer, this is the process of transfer of heat from high temperature system to low temperature system. There must be a temperature gradient. There must be a temperature difference. And usually heat will flow from high temperature to low temperature. So the heat transfer is the movement of heat across the boundary of the system due to temperature differences between the system and the surroundings. And we have looked at the different modes of heat transfer when we were introducing this in pharmaceutical in our introduction to pharmaceutical industry. Then we looked at conduction, we looked at convection, we looked at radiation also. So the process in which there is no transfer of heat between the system and its surroundings is called adiabatic. So there is no transfer of heat between the system and its surroundings. So it's called adiabatic system. So that means if there is no heat, they are in equilibrium. The temperature is the same. If you, for example, want to heat water using another liquid, the temperature, there will be no heat transfer. So the system is called adiabatic. It's called the adiabatic system. So it is called adiabatic process. Now, what is the application of heat transfer? Heat is supplied in order to convert a liquid into vapor. If you want to, for example, dry your extracts, which have been extracted with, say, methanol solvent, and you want to remove off the methyl, the solvent which we use to extract, so that you can remain with the dry extract, then you have to apply some form of heat to the extract so that methyl methanol is evaporated, then it is cooled, if possible, if you want to recover it, and then you'll be able to remain with the extract. So the liquid present in material is evaporated with the help of heating to get a concentrated product. And this one you have given us as for example, in the preparation of vegetable extracts. Now, in distillation, heat is supplied to liquid mixture for converting the liquid into vapor, so that individual vapor components are condensed at another place. So if you want, for example, to separate, to get 96% alcohol, you have to heat to make sure that you remove off the ethanol which boils at 90 and at 76, first boils off. And then when the temperature rises to 100, that's when you can start getting water and in form of steam, which is cooled. And then when it's cooled, you can always get it into another place. But at 76, that's when you can always get ethanol. And this is done by distillation. But also in the production of tablets, heat is passed through a carrier gas over a bed of wet solid mass for achieving dry. Now we shall be looking at some of these bed heat exchangers and what type of carrier gas can you use, for example, in drying these tablets. So the gas comes as a heat, carrying the heat through the tablets, and then they are dried. Now, you also do it in crystallization. When you have saturated solution, the solution is heated to bring about super saturation, where you cannot dissolve any solid in that. So this one will promote crystallization, and you can always be able to filter. When you filter, you remain with the solids, and then the liquid can come down. Remember, the liquid that comes down is again supersaturated. You can still heat so that you can promote crystallization. As you continue doing that, you'll be able to get your dry product. Now, also sterilization. Sterilization of pharmaceuticals. Autoclaves are used with steam as a heating media. Dry heat is used for sterilization of glass apparatus and other containers. So you can have other containers and then you sterilize them. You have the autoclave, you can put their equipment and then heat them and then sterilize them. Sterilization of pharmaceuticals, say in autoclaves and whatnot, is one method of heating where you have to exchange heat. You have to transfer heat from some source so that they can be applied to sterilize equipment. Now, what is the objectives of heat transfer? Now, it's therefore to reduce the heat or the energy loss and making energy utilization more effective. We have some processes that we can do in order to minimize the heat loss. One of them is insulation. So in this case, you reduce the heat that is transferred into other surroundings so that you can bring it into the system. So you prevent it to cross to other surroundings apart from the system in which you have created it for. Now, you can also enhance where it is promotion of heat transfer across a finite temperature difference. You enhance, because of the different surroundings, heat can be lost within these surroundings, but then you can always create a system where you enhance transfer into the system because of the finite temperature difference. And we shall be looking at how we can be able to do this. Now the temperature control, now the temperature of a region is required to be maintained close to the specified value. Through more blood flow, is an example of temperature control. So we can control the temperature through maybe sweating, then blood flows into other regions of the body in order to keep the temperature constant. When you feel like cold, you do some exercises, and therefore you stimulate the blood flow into body organs so that they can produce heat. They can work, and then there is the product is heat, and that heat can make the body warm. So the mechanisms of heat transfer, we have seen that heat must be flowing from high temperature to a region of low temperature. And this one is done through three basic mechanisms, which we saw when we were introducing ourselves to pharmaceutical engineering. So conduction, convection, and radiation. Now, conduction, if we can go into detail with conduction, this is the process in which heat flows in a body, is a process in which heat flows in a body and achieved by the transfer of the momentum of individual atoms or molecules without mixing. So you find that an atom does not move. Instead, there is what you call vibration. In the process of vibration, then heat is transferred. So the transfer from one atom to another within the object by indirect contact with each other. So if there is a solid, the atoms are coupled together because of the vibration of one atom, then the other atom is also affected. It will start vibrating, and that is the process in which transfer of heat is effected in solids. So for example, flow of heat through metal shell of a boiler takes place by conduction as far as solid wall or shell is considered. So the flow of heat depends on the transfer of vibrational energy from one molecule to another. And in the case of metal, it's the movement of free electrons. So it is the vibration of the atoms, and then free movement of electrons, this time not atoms, but electrons, then can be able to transfer this particular heat. In convection, convection is the process in which heat flow is achieved by actual mixing of warmer portions with cooler portions of the same material. So we have something like waves which mix. In the process of mixing, they transfer heat from one region to the cooler part of the region. So it is the heat transfer due to bulk movement within the fluid. And we saw that last time that fluids include gases and liquids. For example, the heat of water, heating water by a hot surface is mainly by convection. But otherwise, we have two types of convection. We have natural convection, and we also have forced convection. Now, natural convection, which is free convection, refers to a case where the fluid movement is created by the warm fluid itself. The fluid movement is created by the warm fluid itself. So you heat at one point, then because of movement, waves, then the fluid next, the region which is cooler, gets the heat. They are telling me that I have less than 10 minutes, but in case we get off, we shall be able to log in again and be able to continue. So the density of the fluid decreases as it is heated. Therefore, hot fluids are lighter than cold, than what? Than cool fluids. Here we have the density of the fluid decreases as it is heated. So that means that we've seen that if you heat, one thing that a fluid, one thing that you do it is that if it has space, it expands. And once it expands and the mass does not change, that means the volume has changed. And you can see that density is mass over volume. So if the mass is constant and the density changes, that means it increases. That means density will reduce. So the density of the fluid decreases as it is heated. Therefore, hot fluids are lighter than cool fluids. That is something very important which I shouldn't have missed. Now, forced convection uses external means of producing fluid movement. Here in free natural convection, you heat at one part and then the liquid starts moving. That's the one which is moving. But now with forced convection, you have a force. You apply some mechanism. You apply, say, a stirrer to make sure that the liquid moves. You have heat exchangers. There is some force, external force that is applied to make sure that the hot fluid moves to the cooler region. So like heat loss from your body is increased due to the constant replenishment of cold air by the wind. So natural wind and fans are the two most common sources of forced convection. So you can have fans. You fan, then brings cold air onto your body, and then you feel like you are cool. You are cooling your body. So in this case, the fan brings in, forces the cool air or the hot air to come into your body. Then the natural wind, as it blows around, you feel that your body is cool. And there is some external convection, external force. Now, with radiation is the energy transfer process in which heat flows through space by means of electromagnetic waves. I was taking some water. So radiative heat transfer occurs when the emitted radiation strikes another body and that heat is absorbed. We all experience radiative heat transfer every day, like solar radiation, which is absorbed by our skin, and that's why we feel warmer in the sun, even when we're in the shadow, than in the shadow. Now, solar waves, solar water heaters, solar cookers, microwave ovens, microwave cookers, we have sonicator bath, and a few examples in which radiation is utilized for producing heat. And most of these are actually found in the production of pharmaceutical products. Here, this is a picture which illustrates the three types of heat transfer. It's not our first time to encounter this, but you can see where radiation, convection, and conduction are actually met. Now, when we come to conduction and we apply in some mathematics, we bring in quite a number of factors. Let's go step by step with conduction. Then when we reach convection, it is the same thing that we shall be able. So we shall not waste a lot of time on looking at some of these equations. Now, look at the thermal conduction. We have seen that thermal conduction is the transfer of heat by microscopic collision of particles and movement of electrons within a body. A body in this case can be a metallic shell, it can be a piece of wood, it can be, but it is thermal conduction. The basic law of heat transfer by conduction can be written in the form of rate equation, where we have that the rate of heat transfer is equal to the driving force divided by the resistance. And note that is equation 1. Now, what is this driving force? The driving force is the temperature difference, or you can call it the temperature drop across the solid surfaces. The greater the temperature drop, or the greater the temperature difference, the greater will be the rate of heat flow. So the driving force is the temperature difference or temperature drop across. So the flow of heat will also depend on the conductivity of the material through which it is flowing. The conductivity of a metallic rod is not the same as the conductivity of a wooden rod. So the rate, the flow of heat, even the driving force, but the rate will also depend on the conductivity of the material. Some glass, for example, is more of a conductor of heat than wood. Yes, it is more of a better conductor than wood. Metal is a far better conductor than wood. So the flow of heat will depend on the conductivity of the material. For example, conduction of heat is faster through an iron rod than through a wooden log. So this factor is represented by the term resistance, which can be quantitatively be expressed by Fourier's law. So in this case, we are seeing rate being driving force divided by resistance. But now resistance is given as thickness of the surface divided by the proportionality constant times the area of the surface. We shall be looking at what we mean by this proportionality constant. By the thickness of the surface, we are going to look at some pictures. So this equation for resistance is obtained from Fourier's law. Now, Fourier's law, that's the conduction of heat through a metal wall. Fourier's law states that the rate of heat flow through a uniform material is proportional to the area and temperature difference or temperature drop, and inversely proportional to the length of the path of flow. Now, that is the rate of heat flow is proportional. This is a sign of proportionality, is proportional to the area through which it is flowing times the temperature difference, which is given as delta T, and then you divide by the thickness. The thickness is the distance through which this particular heat is going to flow. Now, if you take a square metallic rod whose length is 1 by 1, one side is one meter and another side is 1 meter, then the length is set 2 meters. So in this case, the area, because that is proportional to the Are you back?
Yes, we are.
Are you hearing me clearly?
Yes.
Okay. 4 years law states that the rate of heat flow through a uniform material is proportional to the area and the temperature drop. So that's why we have area in meters squared, and then the temperature difference is delta T. So, and it's inversely proportional to the length of path of flow. So we have a rod and we are hitting it at one end and it's going through like a meter. So in this case, the thickness is the meter. So we can see it as the rate of flow is represented as Q. So if we remove the sign of proportionality, we have then Km times A times delta T divided by the length. So Km is the mean proportionality constant, and you can clearly see its units, its SI units. So W is what? M is in meters and K is in Kelvin. So Fourier's law can be applied to a metal wall through which the conduction of heat takes place. So the area of the wall is A in meters squared. The thickness of the wall is L in meters. Then the face of wall, which is on the hot side, that's HH is actually represented on the hot side, where we are actually applying the heat. We are using safe water to heat. And this water is a liquid or a fluid, is the one which is used to heat, and it is applied on one side of the wall. So the heat is actually at a particular temperature. So that side is represented as HH. So it is maintained at uniform definite high temperature, which is T1, and it is in Kelvin. Then the face of wall on the other side, which is on the lower side, because now the other face oh, darling, what's happening? There is someone who has raised their hand, and there is someone who has failed to mute. Can you mute yourself so that we can hear, please? Thank you. So the cold surface, after the heat has gone through a length L, that's where we've called it CC. And that one is maintained at a lower temperature, but uniform. And that temperature is T2, and is also given in Kelvin. So the heat flow will be at right angles to the plane A and is assumed to be in a steady state. So let me just get to that. So in this case, we are having HH. So this is the hot surface, and it is at a higher temperature. Its temperature is T1, and we are having this heat moving through the wall whose length is L. Now, the surface here is the area. That's the area. And this side here is what we've called HH. Now, the lower temperature side is CC. That's why we have called it C. There is this C here. There's also another C around here. So that is the lower temperature. Now, if you consider if you consider the thin section of thickness, dl, we are considering dl at an intermediate point in the wall. The Fourier's law may be one applied will be given as, because we saw that the rate, so by the change, the change heat, because we are looking at this particular section only. So it will be the change in heat in this section, which is delta Q. You divide it by the change in temperature, which gives us the rate. And that one will be applied to Fourier's law. So in this case, we shall have delta Q divided by delta, which is rate, and this one is giving us negative K, which we've called, what have we called it as? We've called it the mean proportionality constant. We've called it the mean proportionality constant. So proportionality constant, which has been given as that. So K divided by the area times the change in temperature divided by the change in distance. So this one here gives us the heat transfer rate. dQ over the theta gives us the heat transfer rate, that the heat transfer per unit time. So the minus sign in this case indicates that there is a decrease in temperature in the direction of flow. If it was to be a decrease in temperature, which is not possible unless you want to remove some heat from the metal, then that's when you can be able to have it as a positive. So it is the minus sign. So in the equation, the T over the L represents the temperature gradient. So that is the temperature gradient. Now for steady state heat transfer, this equation changes to dQ over the theta. So that means that the rate is constant. We are having a steady state heat transfer. So the rate is constant. The rate is the change of heat per unit temperature change. So in this case, we have it as Q. So that's the rate of heat transfer. Then we can always have it as Ka dt dL. Q is, in this case, is the rate of heat transfer, which is in joules per second. And joules per second is usually given as watts. So we can always arrange that particular equation to have it as Q, which is equal to Km A times, that's area, times the temperature change divided by the length through which that particular heat is transferred. So we have our constants as that. So if you rearrange that particular equation, you'll be able to see that Q is equal to delta T over L times 1. No, times there is divided by KMA. So it is actually dividing it by KML. So this one goes up. So this particular equation is actually written in a different way. So equation 7 is rearranged from equation 3 and equation 6. So you should note that. So by comparing, we find that the resistance is given as L divided by Km. So when we were beginning, we saw that rate is given to the driving force divided by the resistance. So resistance is given by that particular equation. So Fourier's law is used to define the resistance in quantitative terms. The thermal conductivity, which is K, is the quantity of heat transmitted due to unit temperature gradient in unit time under steady conditions in direction normal to the surface of the unit area. What do we mean by this? The quantity of heat transmitted due to unit temperature gradient. Unit, that means the temperature is changing by 1 Kelvin, because Kelvin in this case is what we are using as the units. So the change in temperature is 1 Kelvin in 1 unit time under steady state conditions in the direction normal to the surface of the unit area. So it is 1 unit area, but normal, and the temperature change is 1 degree Kelvin, and then the unit time, which is 1 second. And that one gives us the SI units of thermal conductivity in watts per meter Kelvin. So in watts per meter Kelvin, which is really very important. Now, those are the conditions. How do we get resistance? How do we get driving force? And then later we can be able to get the rate of heat transfer. These ones, if you have the thermal conductivity of some materials, you can choose which material will actually be more efficient in, say, evaporating some component out of a mixture of components if you're making drugs, and to not be able to spoil or to denature or to convert the other components. Convection. Convection is a process in which heat flow is achieved by actual mixing of warmer portion with cooler portions of the same material. And we've looked at forced convection. We have also looked at natural convection. And I've already explained those very, very well. So in pan evaporator, convection is set up in the evaporating, so that is forced convection. In general, fluid flow may be described as either laminar or turbulent. This one, we saw it when we were talking about fluids. And when heat is passed through the tube, stagnant films determine the rate of heat transfer. Stagnant fluids, stagnant films determine the rate of heat transfer. You remember when we were discussing fluid flow, we talked of turbulent and then laminar. With turbulent, we saw that the layer along the wall of the tube is actually constant. So we can always call that film stagnant. It is not moving. If it's not moving, then we can treat it as a solid. We shall be looking at it later. When fluids flow, when the fluid flow is viscous, velocity is 0 at actual surface of the wall. So it means that that layer of fluid adjacent to the wall acts as a stagnant film. So comparatively, stagnant film can be observed even in turbulent flow. So that means turbulent flow, we have conduction. Conduction can be observed because we have a stagnant film. It's not moving. We've seen that in convection, one part of water, one part region of hot water moves and hands the heat to another part of cooler region. So if you have it stagnant, that means that heat will be realized, conduction of heat will be realized in this particular stagnant film. So sometimes, scales are deposited on the surface of the metal wall and heat must be conducted through the scales. So in this case, it is conduction which is taking place. So when steam gives up latent heat, latent heat is the heat that is being generated without changing temperature. You don't change temperature, so that's latent. So water will condense on the surface of the vessel or tube. Again, the heat must be conducted through this water film. So that is also through conduction. So for heat transfer in tube, heat must pass through stagnant film by conduction. Yes, can't listen but not hearing. There's someone who has who has put his hand up. Can I have your comment, please? Can't listen, but
Yes. Good evening, sir.
hello, how are you?
I'm right. I would like you to clarify to me what stagnant film means.
Pardon?
I would like to know what stagnant film means.
What is your name again? Because I can see you as can't listen but not hearing.
I'm somewhere.
PHS.
PHS.
PHS. Somewhere who? Can you please answer? Somewhere who? Okay. Now, last when we were discussing flow of fluids, we looked at that fluids can be turbulent or laminar, and the velocity of this flowing fluid through a pipe is highest in the middle of the pipe. Just imagine that it is now the turbulent flowing of the fluid. So the velocity in the middle of the pipe is highest and goes on reducing as you move towards the walls of the tube on both sides of the tube. Now, at the wall of the tube, the velocity is 0. That means that there is a film that is not moving. It is stagnant. So that's what we mean by stagnant film. Are you with me, sir? Samuel? Have you heard that?
Yes.
Have you got it?
Yes. Yes.
Yeah. So that is the stagnant film. Now, we were looking at so those stagnant films can develop into scales, and the type the heat, if the heat is to be transferred from the hot surface through that film, it must be done by conduction. So that is the stagnant film we are talking about. Now, forced convection is a heat transfer convection process in which mixing of the fluid may be obtained by use of a stirrer or agitator, or you can use a pump the fluid for recirculation. Now, consider a case of heat flowing from a hot fluid through a metal wall into a cold fluid. So this is a type of exchanger where you have one tube, you have a tube, and there is another tube that is surrounded. There is a middle tube. Take an example of if we had a sock slate, you have water, cold water, but in the middle there is vapor. Now that vapor is getting cold through glass. You get it? So in this case, that is where we are having a hot fluid, say surrounding, I mean, is passing through a tube that is surrounding another tube through which cold fluid flows. So we are considering that case. So in this case, we are considering a hot fluid through a metal wall into a cold fluid. Now, variation of temperature at specific point is observed. So variation, you can see that there are some variations. We have the hot fluid, which is actually moving turbulently. That means that along this wall, there is a stagnant film. You can see this is a hot fluid. Now there is a temperature, which is TA. We also have the temperature at TB. We also have the temperature at TC. We also have the temperature TD. We have temperature TE and temperature. So we are going to define all those particular temperatures, but note that diagram, that's the temperature gradient in forced convection. Forced convection, where we have a stirrer or an agitator, while the rest of the flowing from a hot fluid to a cold fluid through a metal wall. And the metal wall is this one, which has been indicated. Now, the dotted lines, you can see here the dotted lines, HH, that is the boundaries of the film in on the hot surface, but there is also the boundary on the cold surface, which is CC. That one is also given. Now you see the gradient line TC and TD. You can see here TC and TD. They are actual. So that one is caused by flow of heat, whose conductivity is known, because that is the temperature difference, TC and TD. The difference is through the metal wall, and that one is done by conductivity. Now you can also note that the thickness of the metal wall is L. It is indicated here. Now look at the hot fluid side. To the right of HH, this dotted line here, the fluid is in turbulent flow. On the hot side, the fluid is in turbulent flow. Now, TA is the maximum temperature in the hot fluid, this TA here. And TB is the temperature at the boundary. TB here is the temperature at the boundary on the hot side. It is indeed turbulent. It is turbulent, viscous, and flow. So this one here, the cold one, is turbulent. TB here, the hot surface is turbulent. TB is that one here. Now, TC is the temperature at the actual interface. TC is the temperature at the actual interface. While the curve TA, TB, TC represents temperature gradient from the bulk of the hot fluid to the metal wall. So from TA, TB to TC, that's the temperature gradient from the bulk of the hot fluid to the metal wall. Now, when you look at the cold fluid side, to the left of the line, the dotted line CC, the fluid is also in turbulent form. It is in turbulent flow. So TF is the minimum temperature of the cold fluid. TF is given here, while TE is the temperature at the boundary on the cold surface, while TD is the temperature of the actual interface between the fluid and the solid. So those ones are really very well explained. Now, curves TD, TE, TF represents the temperature gradient from metal wall to the bulk of the cold fluid. To the bulk of the cold fluid. So surface, when you look at the film coefficient, there are sometimes we are going to define. Film coefficient is when you look at film coefficient is the quantity of heat flowing through the unit area of the stagnant film per unit drop in the temperature. So it is a film coefficients, that's what we want. What are they used for? So it is the conductive capacity of the stagnant. So it is if we can have our. So we are going to be applying mathematical things that we did in the conduction, and in this case, we are looking at coefficients which are very well explained. I'm not going through this because of lack of data and the various, but I think when you read through, when I send over the notes, you'll be able to understand. We are not going to finish today this one here until I get more data. So LK, all these calculations are for that, and the overall coefficient is what you will be able to look at. Now, natural convection has been defined, and its application has been well defined in here, which you can be able to read. And we're actually applying forced convection when we are drying extracts in the lab. You can see people who are trying to blow. They are trying to blow using a fan. Some of the liquid extracts, they want to dry them, but they are using a fan. So that is also forced convection, but also you can heat through. You can try to heat so that you can apply natural convection, but at controlled temperatures. So the modes of feed and heat transfer, these ones will give us the types of exchangers we have to use. We have parallel heat flow, we have counter current heat flow. So this variation in temperatures and temperature gradients, they are well explained in these notes. But let's look at parallel heat flow. Parallel heat flow actually can be a very good example is in the distillation apparatus. You have cold water flowing in the same direction as the vapor that is being produced down. So in this case, that one is parallel heat flow. When you have counter current heat flow, you have water flowing in the opposite, or the cooling agent is flowing in the opposite direction from the liquid that's being cooled. And all these ones here have been explained, and the different graphs of indicating the heat flows have been well indicated. So that one is temperature difference when the hot and cold fluids are flowing in the same direction. We have one here. You can see that the hot fluid is coming in while the cold fluid is also coming in. So they are flowing in the same direction. And the calculations there involved are well illustrated in this, and you'll be able to. While counter current flow, the temperature is different. They have the temperature difference here. We have the cold fluid which is coming out, while the hot fluid is actually coming down. So it cools here, while the cold fluid actually raises its temperature. There is a temperature difference between the two, and those ones are well explained. So we shall begin maybe with radiation next time when we hear from each other. This one here is going to be not tomorrow. I know we have a lecture in this, but I will not be able to attend it. I just want to wish you the best until we meet on Tuesday next week. Have a good time.
Webale muno.
You too.
Hello?
Yes.
Yeah, you can wish me good evening, please. You can unmute and wish me good evening.
A good evening.
Yes, thank you.
Good evening.
Yes.
Good evening to you too.
Wish you a fantabulous evening.
Thank you, Okalebo.
Good evening, sir.
Darling, have good evening too.